Today we're going to do the vertical circle problem. As we can see in our diagram, we have a little car that is moving around a circle. So we visualize like a steel cage or something the car is going around, or maybe a loop. And the first step is to draw a force diagram for the car at each the bottom and the top. So let's do the bottom first. Let's make this one the bottom red. And the force on the car when he's at the bottom are obviously mg, the force of the earth pulling down, and then since he's at the bottom of the circle, the track or the cage or whatever, the road, has to push him up. That's a force exerted by a surface. We call that the normal force. Now, in this case, conceptually speaking, our car is in circular motion, and if you're in circular motion, there has to be an unbalanced force, and it has to point toward the center of the circle. And in this context, obviously, the center of the circle is above the car. Therefore, the normal force has to be bigger than the weight. If we draw a force diagram for the car at the top of its loop, we'll make this one green. What we'll notice here is that the earth is still pulling down with the same amount of force. That's still mg. But because now it's underneath the track, the only way the track or the cage or whatever you want to call it can push it is in the down direction. It's still a normal force. Now, I happen to draw it bigger, but we don't actually know the size of the normal force. It might be smaller, it might be bigger, it might be the same size, and we may make some edits to this later. But right now we can see that both the forces are down. This is still consistent with our understanding, because if it's in circular motion, the unbalanced force has to point toward the center, and the center relative to this car is down, and since both forces are down, it's still pointing toward the center. So the question is, how does our driver feel, or how does our rider feel when he's at the bottom? The question is, does he feel heavy, light, or normal? So let's talk about the bottom. Let's talk about the bottom. When he's at the bottom, okay, we know he's accelerating, and so the acceleration is equal to the net unbalanced force over the mass. No big deal. But because he's in circular motion, we say his net force is also known as his centripetal force. From the lab, we know that the centripetal force is equal to mv squared over r is the centripetal force. So how can I express the net force? Well, in this context, the net force, given this force diagram on the side here, is normal minus the weight. In order to keep our values positive, we always do big minus little. So we do big minus little, normal minus weight. Since the net force is a centripetal force and the net force is n minus mg, I can set those equal to each other, and I end up with this expression, mv squared over r is equal to n minus mg. And when I look at this expression, what I realize is that if I solve for the normal force is equal to the addition of this centripetal part, the mv squared over r, and the weight. So obviously the normal force is bigger than the weight by itself, which is consistent with our force diagram. And if I want to find out how many times heavier he feels, we always compare the force that the road supplies, or in this case, it's the seat on him compared to his weight. So again, how many times heavier? You do normal divided by the weight, and that gives you your answer, how many times heavier. We can continue this idea. To try to figure out how the rider feels when he's upside down. So let's take the green one. If I start with the same process, that the acceleration is equal to the net force over the mass. If I express the net force this time, the net force on the rider when he's at the top, this time it's equal to the N plus the mg. And this time we're adding them together because they're in the same direction. In the first one they were in opposite directions, so we subtracted. This time they're in the same direction, so we add them together. If the F net is still equal to mv squared over r, it's equal to, this time, N plus mg. If I want to solve for n this time, n would be equal to mv squared over r minus mg. And so if we knew the speed and the radius of our circle, we could then figure this out. And if n was greater than mg, we would know he felt heavier, and if n was less than mg, we would know that he felt lighter. The last question, and the real question, is what is the minimum speed that the rider could go and still stay on there? The minimum speed the rider could go and still stay on there. Well, to do the minimum speed, what we can do is we can start with the same conceptual framework that we used for the how does he feel going through the top of the loop. If I use the same conceptual framework here, the net force is equal to N plus mg. So mv squared over r is equal to N plus mg. And as you go slower and slower, the left side gets smaller, the right side has to get smaller, and what that means is that the normal force gets smaller and smaller. And at the V minimum, the normal force is actually equal to 0. And if that's true, then our equation works out mv squared over r is equal to mg. If the m's magically go away, I end up with v squared is equal to rg. So the v min is equal to the square root of rg.